Students, welcome to my channel. In this video, I'll be explaining about the thermal degradation, that is one of the types of the polymer degradation. In the last video, we started the polymer degradation and we studied the introduction and the mechanism by which the polymer can undergo degradation. Okay, now in this class we will be studying about thermal degradation. Okay, this is one of the types of polymer degradation. Remember, thermal degradation is influenced by, influenced by heat. Okay, the thermal degradation means it is the degradation of the polymer that is influenced by the heat. Okay, and this thermal degradation, it may follow, either of the mechanism. Okay, in the last video we studied about the two types of mechanism by which the polymer can undergo degradation. Okay, what are the two types of mechanism? It may follow either chain end degradation, and it may undergo random degradation. Okay, these are the two types of mechanism by which the polymer undergoes degradation. Okay, in case of chain end degradation, what we get? We will get the pure monomer. While in the random degradation, whether we get monomer? No, we do not get monomer. Okay, monomer is not formed. Instead, what is formed? We will get the product with the lower molecular weight. Okay, in chain end degradation we will get the pure monomer, but in case of random degradation we do not end up with the monomer, but we will end up with the smaller product with the lower molecular weight. Okay, now this thermal degradation can follow any of this mechanism. Okay, if it follow chain end degradation, we will get monomer. If it goes through this random degradation, we will get the product with a smaller molecular weight. Now, this thermal degradation depends on certain factors. Okay, the thermal degradation of the polymer depends on certain factors. Let's see what are the different factors by which thermal degradation depends. Okay, the factors. Okay, we will study the factors. We have 4 factors by which the thermal degradation depends. Okay, first one is the stability of CC bond. The stability of CC bond. Okay, we know that most of the polymer has CC bond in the backbone of that chain, right? So the stability of that CC bond in the polymer backchain decides the thermal stability of that polymer. Okay, let me take an example of polyethylene. Okay, polyethylene, you have this unit. Okay, like this, you have this unit. Okay, this is polyethylene. Now I write polypropylene. Okay, it continues like this. Polypropylene is this CH3, and it continues like this only. Okay, this is polypropylene. And one more, I take example of this one. CH3 and CH3, and it continues like this only. Okay, this is polyisobutylene. Okay, this is polyethylene, polypropylene, polyisobutylene. So what you can see, as move from the left to right, here you have H as a substituent group, but here what you have, you substituted CH3 in the place of H. Okay, but in this case polyisobutylene, what you done, you replaced both the H and replaced CH3 group and become polyisobutylene, right? So now what happened from moving from polyethylene to polyisobutylene? The bulkiness of the substituent group increased. Here H is not bulkier, but whenever you substitute CH3 in place of H, that become a bulkier. And if you replace both of the H by the CH3 group, once again the bulkiness increases. Okay, bulkiness increases from polyethylene to polyisobutylene. So if the bulkiness of the substituent increases, the CC bond strength decreases. Okay, if bulkiness of substituent increases, then what happens? The CC bond strength decreases. Okay, if CC bond strength decreases, what happens? It is thermally least stable. Okay, therefore it becomes thermally least stable. Okay, least stable. So now tell me, among these three, which one is thermally least stable? Thermally least stable is this one, polyisobutylene. Why? Because here you have CH3, 2CH3 substituent that is bulkier than hydrogen. So this polymer is bulkier when compared to polyethylene. So CC bond strength in this case, polyisobutylene, is least stable, and as a result thermally this polymer become least stable. Okay, if I write the thermal stability, polyethylene, okay, polyethylene is more stable, okay, compared to polypropylene, and polypropylene is more stable than polyisobutylene. Okay, this is the order of thermal stability among these three polymers. Okay, polyethylene is more stable because it in this case CC bond strength is greater because H is not bulkier group. Okay, that is what you need to remember. Okay, now if I have this, okay, sorry, H. Okay, what is this polymer? This is polyethylene. Okay, polyethylene. Now what I do? I replace this H by phenyl group. Okay, phenyl group is C6H5. Okay, phenyl group. Then what is the name of this polymer? This is polystyrene. Now what I do? I replace another H . In this example, what I do? I replace this H by CH3 group. Okay, and here once again you have phenyl group. Okay, in this polymer all are H. Here what I did, I replaced H by this phenyl group, and in this example I replaced this H by CH3 group. Then what is the name of this polymer? Tell me. This is poly alpha methyl styrene. Okay, this is poly alpha methyl styrene. Now can you tell me, among these three polymer, which one is more stable? Which one is more stable? Polyethylene is more stable. Why? Polyethylene, in this case, all the substituent is not bulkier, right? These are light in nature. And if you go to the polystyrene, C6H5 is the bulkier when compared to hydrogen, correct? So if the bulkiness of the substituent group increases, what happens? The CC bond strength decreases. Here you have two bulkier groups, so this CC bond strength here, it is least stable. As a result, this polymer become least thermal stable. Okay, so what is the order? PE is more stable than polystyrene, and that is more stable than poly alpha methyl styrene. Hope it is clear. Okay, this is point number 1, the stability of CC bond. Okay, the next point we will see. Okay, second point. Now, not all the substituent reduces the thermal stability. Okay, that is the second point, thermal stability. Well, okay, not all the substituent group that reduces the thermal stability. For example, if you consider this, what is this polymer? This polymer is nothing but polyethylene. Okay, polyethylene. Now what I do is I replace this all the H group by the fluorine atom. Now tell me, what is the name of the polymer? If I replace H by the fluorine atom, so what I did, I just replaced H by the fluorine atom and I got this polymer. What's the name of this? It's a very famous Teflon. Okay, it's the name of this polymer is Teflon. Okay, or it is also called as polytetrafluoroethylene. Okay, that is another name. A common name is the Teflon. Okay, now here you have the substituent fluorine, right? So among these two, which one is more stable? Okay, that is the question. The Teflon is more stable when you compare to polyethylene. Why? Why? Reason is, okay, reason because fluorine. Here you have the fluorine. What is the nature of fluorine? The fluorine is most electronegative, no? Most electronegative atom. So fluorine is most electronegative. As a result, what happened? The CC bond strength become exceptionally stable. Okay, since F is most electronegative in the nature, the CC bond strength become greater. Okay, if the CC bond strength become greater, what happened to the thermal stability? It definitely increases. Okay, thermal stability of Teflon is more when you compare to the polyethylene. Okay, and it is found that in this case, Teflon, the CC bond dissociation energy is around 105. Okay, it is, sorry, 108. Okay, 108 kilocalorie per mole. Okay, in the case of Teflon, the CC bond dissociation energy. Bond dissociation energy means what? It is the amount of energy that is required to break the bond. Okay, how much energy is required? 108. But in this case, polyethylene CC bond dissociation energy is only 88 kilocalorie per mole. Okay, by this also, you can make out that the Teflon is more thermally stable when you compare to that of polyethylene. Okay, this is a point number 2. Okay, if there is any doubt, let me know. Okay, the third point. Third point is presence of aromatic ring or aromatic group in the polymer back chain. The polymer back chain. Okay, now suppose if there is a presence of aromatic ring in the polymer back chain, then what happened to the stability? Okay, remember, if there is a presence of aromatic ring in the polymer backbone, then that polymer will have very high thermal stability. Okay, for example, if you consider this polymer, O C double bond O. Okay, what is the name of this polymer? Okay, this is N. What is the name of this polymer? This is polycarbonate. Okay, polycarbonate. Now this polymer is highly thermal stable. Why? Because in the polymer backbone, what you have? You have the benzene ring or aromatic ring. So if there is a presence of aromatic ring, the thermal stability increases. Okay, and I give another example. This is example number 1, and you have another example also. Okay, it continues like this. So what is the name of this compound? Tell me. It is polyphenolane. Okay, phenylene. Okay, this is the polyphenylene. This is much more stable when compared to polycarbonate. Why? Because in here all the atoms or all the groups in the polymer back chain is made up of aromatic ring only. Okay, that's the reason why polyphenylene is most stable. Now if you consider one more example, this one. Suppose if you have like this, okay, here substituent is fluorine atom instead of hydrogen. Okay, in the polyphenylene all are H, right? Here it is H. Even though I did not write anything, that that is understood that it is containing H. Now what I did, I replaced that H by the fluorine atom. Okay, everywhere F. Now tell me whether it is stable. Yes, it is highly stable when compared to these two. Okay, why? Because one reason is that in the polymer back chain, it consists of aromatic ring only. Then also it has the fluorine atom, right? The fluorine atom is electronegative. I told earlier only, if there is a presence of electronegative atom, then the its thermal stability will be greater. Okay, so this type of polymer will have greater thermal stability. Okay, what's the name of this polymer? It is polytetra fluorophenolane. Okay, this is the polytetrafluorophenolane. This is most stable when you compare these two. Okay, this is point number 3. Any doubt? If there is any doubt, let me know, okay? Okay, we will look into the point number 4 now. Now, if there is a presence of oxygen in the polymer backchain, what happens? Okay, the presence of oxygen in the polymer backchain, okay, polymer backchain or backbone, whatever, okay, backbone of the polymer chain. The presence, if there is a presence of oxygen in the polymer backchain, then it will be thermally least stable. Okay, the thermal stability decreases. The thermal stability decreases. Okay, if there is a presence of oxygen in the polymer backchain, then its thermal stability decreases. Okay, one of the example is polyethylene oxide. Okay, you have this structure CH2, CH2O. CH2, CH2O, it continues like this. Now in the polymer backchain, what you see the oxygen, right? If there is a presence of oxygen in the polymer backchain, its thermal stability will be very, very lower. Okay, this is point number 4. Okay, we have one more point, that is point number 5. Okay, there are some reaction that involves the polymer degradation by the breaking of the substituent group, but not the main chain. Okay, what did I say? There are some reactions that involve polymer degradation by breaking the substituent group but not the main chain. Okay, we will understand what that means by taking an example of PVC. Okay, PVC is polyvinyl chloride. Okay, the thermal degradation, okay, the PVC occur at 200 degrees Celsius. Okay, the thermal degradation of PVC occur at 200 degrees Celsius and it liberates HCl during the degradation. Remember, PVC undergoes degradation at 200 degrees Celsius and it also liberates hydrogen chloride gas during the degradation. Okay, now to understand this degradation of PVC is not easy. Okay, it is a difficult pathway by which the PVC undergo degradation. But anyway, scientists have been postulated that there is some free radical that plays an important role in the degradation of PVC. Okay, so that free radical is there. No, that free radical is generated because of impurity or maybe because of reaction mixture also. Okay, so it is not sure that that free radical is generated because of impurity or it is because of reaction. Okay, that is still not known, but anyway they postulated that the mechanism of PVC degradation involves the free radical in it. Okay, we will see how it is. Okay, first I write the structure of this one, PVC. CH2, CH, Cl, CH2, CH, Cl, CH2, sorry, here you have CH, Cl, etc. Okay, this is the PVC structure plus R dot. Okay, R dot is the free radical. This is a free radical. I told this free radical may be generated because of impurity present in the system or maybe because of reaction only. Okay, that is still not understood, but anyway we will write it as R dot. Okay, now what is the mechanism is that this free radical generated, no, that will abstract the hydrogen from the methylene group. Okay, methylene group is this group. Okay, CH2. Okay, this is what the methylene group is mean. Okay, here you can see the methylene group, here is methylene, right? So this free radical, what it will do, it will take up the hydrogen or abstract the hydrogen from the any of the methylene group. Okay, for instance, I imagine that this R dot is abstracting the hydrogen from this methylene group. So what happened? CH, okay, CH, Cl, and this free radical is there, no, that will now goes with this carbon. Okay, whenever R dot abstract the hydrogen from this methylene group, that free radical go with that carbon atom. Okay, CH2, CH, Cl, CH2, CH, Cl plus RH. Okay, this R dot abstracted hydrogen from this methylene group, and whenever it abstracts the hydrogen, what happens? The free radical will shift to that carbon atom. Okay, now in the next step what happened is that the beta chloride, okay, or chlorine atom. This is alpha, okay, this is alpha carbon, this is the beta carbon, okay. The chlorine that is present at the beta carbon, okay, that will be labile, or it is least stable, okay, least stable. Okay, understood what did I mean? This one, and this is the beta carbon, and the beta chlorine atom will be least stable or labile. Okay, it will try to go away, or it will try to detach from the system. Okay, how it detaches we will see. Why it detaches? Because to give the stability to the structure, that's it. Okay, you have this, okay, free radical and CH. Here you have chlorine, no, I told that is least stable, that leaves the system. How it leaves the system? By homolytic cleavage, okay. This bond is there, no, that will breaks homolytically like this, okay. This Cl chlorine atom will liberate as the chlorine free radical, and this carbon is also now have the free radical, okay. CH2, CH, Cl, CH2, CH, Cl plus Cl free radical. Understood? What did I write here? This bond cleaves homolytically. We know that homolytic cleavage will generate free radical, right? We know that this bond is made up of 2 electrons. 1 electron go with the chlorine atom like this, and 1 electron goes with this carbon I written here. Now what happened? This free radical and this free radical combines to give the double bond. CH, double bond CH, CH2, CH, Cl, CH2, CH, Cl and Cl dot. Okay. Now what happened is that this Cl is there, no, that now attacks any of the methylene group. Okay, here it is a methylene group, here is also methylene group. Of course we have other methylene group, but I did not write. Okay, now this Cl is there, no, that will. Now, this Cl can abstract the hydrogen from this CH2 group or this, okay. Imagine this Cl is abstracting hydrogen from this methylene group, okay. Okay, so what happen if it abstracts hydrogen? It become HCl, right? I'll write here CH, double bond CH, CH. Okay, now initially it was CH2, now I write CH because one of the hydrogen is abstracted by this Cl. Okay, and what happened? The free radical over this Cl is now generated over this carbon, and CH, Cl, CH2, CH, Cl plus HCl. Okay, this is what I mean. Okay, during degradation of PVC, HCl get liberated. No, this is what the mechanism is. Okay, now which is the beta chlorine? Beta chlorine is this is alpha, this is beta. This chlorine is labile. Okay, I told here only beta chlorine is labile. It try to detaches from the chain. So what happened, tell me? CH, double bond CH, single bond CH, free radical, single bond CH, it detaches, no, generation of free radical take place. CH2, CH, Cl. Okay, same mechanism I am writing again and again. Okay, now this free radical combine like this. What happened, tell me? There is a formation of double bond. Okay, CH, CH, double bond CH, CH2, CH, Cl. Okay, it continues like this only many times until all the chlorine atom detaches from the chain. So what you can see in here is that there will be a generation of double bond in the alternative position. That means a conjugated double bond will be generated. Okay, this is how the PVC undergo degradation. Okay, remember one thing, the PVC is usually a colorless. Okay, the PVC is colorless in nature, but it may get some colors, like it may get yellow color, or it may get orange, brown. Okay, that is depend upon degradation. Okay, PVC as such is colorless, but during degradation what happens, the PVC color may changes to yellow, orange or brown. Okay, that is depending upon the degradation. Okay, degree of degradation. Okay, now I told that during the degradation of PVC, what is liberated? HCl gas is liberated, right? What is the role of this HCl gas? The role of HCl gas is it act as catalyst. Okay, the HCl gas act like a catalyst here. Okay, so during the PVC, if the HCl gas liberated, that HCl gas speed up the degradation process. Okay, degradation of PVC. Understood? If the PVC undergo degradation, HCl gas is liberated, and that HCl gas speed up the degradation of PVC. So now to stop the degradation of PVC, what I should do? I should remove the HCl that is formed. So to remove this HCl, what I can do is I can add stabilizer. Okay, I can add stabilizer to PVC. Okay, add stabilizer to PVC just to remove the HCl so that degradation process stops. Okay, what are the stabilizer that can be used? We will see. The stabilizers the sodium carbonate, and some salts of calcium or barium. Okay, or we can use epoxidized vegetable oil, okay, etc. Okay, all these are the stabilizers that is commonly used in the PVC. Okay, so we will see what happen if I use the stabilizer. Okay, mechanism of stabilization. Okay, now R okay, this is epoxidized. Okay, epoxidized vegetable oil. Okay, now this is the stabilizer. Okay, now what it will do, we will see. HCl. Okay, HCl is the gas liberated during the degradation. This is the stabilizer. We will see how stabilizer will remove the HCl. What happens is that this bond is there, no, that bond clips, and what happens is that this H goes with this oxygen and this Cl goes with this carbon, like this. OH, okay, and CH, Cl, and R. Now HCl is removed, okay, like this. Okay, HCl get removed by the stabilizers. Okay, one of the famous is epoxidized vegetable oil. That is the well-known stabilizer for PVC. Okay, that will remove the HCl. Okay, like this. Okay, this is what the mechanism is. Okay, this is about the thermal degradation. If there is any doubt in this lecture, let me know in the comment section. And if you like this video, please like it, and subscribe to my channel, and please share. Thank you for watching.